Hello, my name is Mackenzie Maxwell, and this is my Lines of Charge lab. First up, we have the introduction, where the purpose of this lab was to produce a computational model of two charged tapes exerting electric force on each other, and then use this model to estimate the amount of charge on each tape necessary to float above one another. Unlike Lab 1, the charges will be distributed evenly across the length of the tape instead of just a point charge, and then we will use this assumption for the glow script model to create the computational model of the evenly distributed charge. From Lab 1, the two pieces of charge repelled each other while also being attracted to other negative objects, indicating that it has a positive charge, and the value of these values from Lab 1 versus Lab 2 differ, with the results being from Lab 2 being of increased magnitude. In Lab 1, it was 1.4 e 10 to the negative 8 coulombs. In Lab 2, it was 2.16 10 to the negative 8 coulombs. These are the fundamental concepts and assumptions used in this lab. First up, we have Coulomb's law, which is our force, which is K times Q1 times Q2 over R squared. This could also be in a vector form, adding R hat. And then we also have the electric field, which is the point charge formula, which is what we used in Lab 1, which is E equals K times Q over R squared R hat. And then we have the electric field of the rod charge, which is that's the top left, which is KQ over R square root R squared plus L divided by 2 squared. This is also with R hat. We also have the force of gravity, which is F equals negative mg, which G is negative, or G in this case is magnitude, so it is 9.81. And we also have the force and electron field relationship, which they equal each other. We're going to use superimposition to figure out what the electric field is for the rod. The experimental design of this lab will be exactly the same as Lab 1, only in this case the tapes will be treated as rods versus being point charges for calculation purposes. The assumptions for this particular part of the lab is we're going to ignore air resistance. The tape will not be used as a point charge, it will be used as a rod charge. The charge is evenly distributed across the length of each tape, and the tape pieces can be separated into segments of equal charge, and the sum of these segments is the total charge. The initial conditions are as follows. There are two pieces of tape, approximately equal in length, are neutral or placed on a third piece of tape on the table. The length of the tape as found from Lab 1, which is 0.201 meters, the width of the tape is 0.031 meters, and the distance between A and B tape as seen on the diagram to the right is 0.021 meters. Here are my calculations to find the charge of the tape by using it as a rod charge. We have F net equals 0 since the tape is stationary, and so we have mass equal, we have the force of gravity equals the force electric, which is mg equals the rod charge formula. And then we go all the way down and we find that Q is equal to 2.16 times 10 to the negative 8 coulombs. With these calculations in mind, we move on to the glow script. On the top right box, we have our G and we have our K constant, which is 9 times 10 to the 9th. And we also have our mass, which is what we found in Lab 1. We have our Q, which is what we calculated for in the slide previously, the length and the distance between each tape. We also have our E field calculations are as followed, with these calculations being placed in that way. And then we also have, on the bottom picture below, we have a few more glow script calculations as well to inevitably get our diagram that will be shown on the conclusion slide. As seen to the left of the screen, we have two diagrams down with the glow script code. The leftmost one would be from Lab 2 and the rightmost one would be from Lab 1. The Lab 2 has a multiple charge angles or multiple charge direction all the way around. So speaking of the segments of the line charge, you can see that with the blue line with an E net or F net pointing in the upward direction, and then on the right we have just a singular charge because it is a point charge. The results via observations are exactly the same as the Lab 1, and the conclusion is using the distributed charge model instead of the point charge model, which is also the rod. For the distributed, calculations will be more accurate in estimated magnitude of the rod line charge for an object with the length of the tape. These inconsistencies could have been with the point charges in the model, the physical experience, necessary handling of the tape during setup, and also incorrect assumptions. If the model is based on a single point charge, it would be the same magnitude from the charge of Fab 1, which is 1.4 e to the -8 coulombs, and the rod charge from Lab 2 would be 2.16 -8. This number is from the calculation I've completed in the previous slides. These estimates differ because each method uses a different approach that results in a different level of precision. The rod charge method allows for more precision compared to the point charge method because it uses smaller step modeling, similar to the precision using calculus to determine the area under the curve.